Thank you. Okay, I think my mic is working okay. Yeah, thank you guys for coming. I hope this will be interesting and informative. So what I'm going to talk about here is some of the ongoing performance work, both from the last few versions of Spark when we introduced Project Tungsten, and the work we've been doing recently in Spark 2.0 to continue that effort. So first, what's going on? What's the motivation for doing some of this work? So first, let's take a look at the hardware trends over the last 6 years. So in 2010, roughly when Spark started, storage was providing about 50 megabytes per second in I/O throughput. Networks, we had 1 gigabit network, that was very common, and CPUs are running at about 3 gigahertz per second. If we fast forward that to today, the landscape has changed quite dramatically for storage and network, with storage offering you 500 megabytes per second of I/O throughput in SSDs, and the network being 10 gig E being extremely prevalent, particularly in data center settings. But CPU, on the other hand, has not improved nearly so much. And we see an order of magnitude improvement in I/O availability, but roughly maybe 30%, something in that ballpark, for CPU. So this change in hardware landscape means that we really need to revisit some of the core performance characteristics of Spark to make sure that we're able to take advantage of these modern hardware trends and provide the best general purpose analytics engine. So in addition to the hardware trends, there's been other things that have been going on that make this even more pronounced. So Spark has historically been optimized for I/O. There are many techniques we have done to do so. To reduce disk I/O, for example, we prune unnecessary input data, so that can dramatically reduce the amount of disk I/O we need to do. And in 2014, as part of the work to set the sort record, we rewrote the network layer, meaning that the network stack is much more efficient and modern. At the same time, there have been developments across the Hadoop ecosystem to improve data format density. So in particular, formats like Parquet or ORC mean that there's less need for as fast disk I/O, right? A 10 megabyte Parquet data set is much larger, more number of rows than a 10 megabyte JSON file. So for that reason, we're able to kind of push more and more of the bottlenecks onto the CPU, right? So the hardware has gotten better on the I/O side, and the software has improved most in the I/O side. And this means that CPU is increasingly the bottleneck, and some of these trends we expect to continue. So that's really the genesis of Project Tungsten. For those of you who have been to these similar talks in the past, this should look very familiar. So the goal here is that we want to substantially improve the memory and CPU efficiency of Spark's core execution engine and push the performance closer to what the hardware can provide for us. And this is both to address the hardware trends as well as to kind of set us up for what we think will be hardware trends in the future. And just to note here that the emphasis here is just on the core execution engine. So we're not looking at things like the Catalyst planner and things like that. So this work so far, as I said, is, oh man. I'm not sure what that is. All right, let's hope that doesn't happen again. So in phase 1, so this is the work done in the last few 1.0 release, or 1.x releases. We focused on improved memory management. We've built the foundation to support runtime code generation, and we've implemented a few cache-aware algorithms to better take advantage of the hardware properties. And most of the work that I'm going to be talking about today is what we're saying phase 2, where our goal is to make Spark run an order of magnitude faster, 10 times faster, using these two techniques, whole stage code generation and vectorization. So just a very, very brief summary of phase 1. I think there are slides that describe this in detail that you can find. So 3 things that we looked at. So to improve the memory usage, we did manual memory management instead of relying on Java objects. So this means that we're reducing the memory footprint, since Java objects tend to be a little bigger than they need to be, reducing the issues with garbage collection. And we do this using Java unsafe and off-heap memory. We did some initial work with code generation for expression evaluation, and I'll be describing that in detail, but that reduces virtual function calls and interpretation overhead when evaluating expressions. And then lastly, we did some work to improve the sort performance by implementing a cache-conscious sorting algorithm And that eliminates some bad memory access patterns, giving us a lot of performance benefits. And we've learned from those techniques, and we'll apply them in the future. So phase 2, how are we going to try to make Spark 10 times faster than it is today? So going back to the fundamentals. So I argue that for performance improvements as dramatic as that we're going for, kind of the traditional techniques typically don't work very well. So by traditional techniques, I mean you fire up Spark, you run a profiler on it, you see what you can do, and you try to shave off the pieces that are slow. So as an example, to get a 10x improvement, we would need to find all of the hotspots that together add up to 90% of the current time and make that instant. And that's really not practical with profiling techniques. Right? Profiling techniques, you typically shave maybe 20% here, 10% there, something like that. And then in contrast, if we want 2 orders of magnitude performance improvement, we would need to find the top 99% hotspots, which is not particularly practical. But we know that systems can offer performance benefits like this. For example, Spark, or originally compared to MapReduce, right, offer 2 orders of magnitude performance improvement. So there are ways to do this. How do we get there? So this work started maybe a few months ago, and we decided to look at performance bottom up. So how fast should the system be able to run if we just kind of relied on back of the napkin arithmetic? So as a motivating example, here is one query. This query is very straightforward. We're just scanning a single table, and we want to count the number of elements where this particular attribute is 1,000. So the picture on the right, this is the current Spark SQL physical plan. So data flows from the plan bottom up. So we first scan the data, then we filter for things that are equal to 1,000. Then we project, meaning we drop the column because we no longer need it. It was only necessary to evaluate the predicate. And then we finally just add up the results. So pretty straightforward query plan. How does Spark SQL evaluate this right now? So Spark SQL uses a traditional database technique that's called the Volcano Iterator Model. So it means that every operator, all the boxes I showed on the previous slide, implement this iterator interface. So an example of this is the filter code on the right. This is not quite exactly how it's implemented in Spark right now, but very, very close to it. And essentially the idea is that every operator reads the value from its child, then does some processing, and optionally returns one or not. So in this case of the filter, in red, that's the call to get the value from its child. And the beauty of this, it's very simple. Every operator is just an iterator, and it's very, very composable. But the downside of that is this is not necessarily the most CPU efficient way to run. So here are some of the downsides with respect to performance of the iterator model. So it's many virtual function calls, meaning you're agnostic to the operator below you. You don't know where the row is coming from, and meaning that at runtime, it's all dynamic dispatching, and it's unable to take advantage of some of the other modern CPU techniques. The second is that there's a very standard format, this row format, that exists between all the operators, and that means writes to main memory. Essentially, you read a row in, then you produce a new row, and you send that to your parent, your caller. And similar to how Spark removes writes to disk over MapReduce for performance improvements, this suffers from problems of having to write all the intermediate results to main memory. Right? Essentially, every row between every operator goes through main memory. And then thirdly, this style of code is very confusing for the compiler and the hardware. That means that we're unable to leverage a lot of modern techniques, in particular auto-vectorization, pipelining, prefetching, branch prediction, instructional parallelism, all this kind of good stuff, right? All of the stuff that modern chips are improving quite dramatically. So instead, what if we did a different exercise and we hired a first-year college student to implement this query in Java, right? What would she come up with? And actually, the answer here is really simple, right? Here is roughly how you would implement this in Java, and it's more or less a one-to-one translation of the SQL code. So, we're just in a loop, evaluating the predicate and counting. And this already is much simpler than the filter code I showed you before, and this implements the entire query logic, right? Not just the filter, this is doing essentially all the parts of it. Furthermore, how do those two compare in performance? So we ran this experiment, and this is just running single-threaded, right? The details of the numbers don't matter. But Volcano, in this case, we get roughly 14 million rows per second. This is kind of end-to-end query throughput. And the version that I showed you, that gets 125 million rows per second. So almost an order of magnitude implementing kind of the simplest way possible, right? So there's something really interesting going on there. So why does this work? So we already talked about some of the issues with Volcano, and the handwritten code it does exactly the work it needs to do, right? Everything is necessary and sufficient. No virtual function calls, data stays in CPU registers. The code is simple, meaning that we're able to maximize the benefits of the compiler and the hardware, right? That code, if you look at the generated assembly, does do loop unrolling and does do vectorization, but you don't need to do any of that hard work yourself. That's kind of what the tooling is able to do if you feed it input that's simple enough. And kind of the key takeaway is at the bottom. What really is the insight here is that the handwritten code is taking advantage of all the information that is known, right? It is designed specifically to run that query and nothing else, and with that additional information, you're able to get much simpler code that runs much, much faster. So this is a technique that's become popular recently in the database literature, and it's called full-stage code gen, right? In the database literature, we've gone back and forth on should we generate code, should we interpret code, and with some of the modern tooling, code generation is getting popular again. So the idea here is that, okay, we want that simple code both for its simplicity and its performance benefits. How do we generate that at runtime? And the idea is that we're going to fuse the operators together, right? So I showed you that filter code, and that's kind of the general purpose filter. But instead, what we're going to do is we're going to identify chains of operators together, and at runtime, compile them into a single function. So we're going to generate the code that is to be run at runtime. And the key here is that we want to provide the functionality of a general purpose SQL engine, right? We can't handwrite the code to evaluate your query, but we want the performance of a hand-built system as if it was just running your workload, right? Kind of the best of both worlds. So as an example, here on the left, this is if you go to the Spark debug page for Spark SQL, what the query plans look like. So in this particular case, the query is a little bit more complicated. We're doing a join with some filters and then aggregation. So in the first phase, we combine operators into whole stage pipelines. So in this particular case, this is the transformation where we've identified 2 pipelines. So we're going to basically, inside each of those blue boxes is an entire pipeline, excuse me. And at runtime, we're going to combine them into a single generated Java function. And there are different rules on how we split up those pipelines. So after we do that, we're going to take a single pipeline and we're going to, at runtime, generate the Java code on the fly that exactly evaluates that. So this is roughly color-coded, and you kind of generate it inside out, if you will. So essentially, the aggregate generates the state and the code to evaluate it, similar for the project, the filter, and the scan. Okay, so that's one technique. The other technique that we're going to talk about is improving Spark SQL's in-memory representation. So there are things that we can't fuse because we won't see any benefit, or they're incredibly complex. So the whole stage code gen technique works particularly well when the operations you want to do are simple over a large data set. And this is extremely common, right? Most predicates are simple. Most of the time, you're not running a regex over a column. Kind of the whole point is relatively simple computation over a large amount of data. But there are many cases where we can't simply fuse the entire computation into one function, and that may be because a component is particularly complicated, for example, parsing CSV or Parquet. We always can't have the pipeline extend across physical machines, right? So we can't do the computation across the network. And then there are cases when we're integrating with third-party components, so we can't integrate their code into our generated code, right? An example of this is calling out into Python or R, or using TensorFlow, or offloading the computation to the GPU, or reading from Spark's columnar cache, right? We see these as components kind of outside of the operator pipeline. So to address some of these problems, we need to improve Spark's in-memory format. So kind of the key here is that Spark in the 1.x releases use a RowBased in-memory format. So in this case, my data has an integer column, a string column, and then a floating point column. So in a RowBased format, those are arranged sequentially, right? So you have an int followed by a string, followed by a float, and then on to the next row. In the columnar format, we simply take the transpose of this. So all of the integers are packed contiguously, followed by all the strings, and then followed by all the floating point numbers. So this is a technique that's pretty common, particularly with on-disk formats such as Parquet, but you'll see that those benefits extend even as the processing in memory format in many ways. So why? So the first, this is kind of the typical benefits you get from the storage perspective. It is more storage efficient, it's more dense, you don't need padding between values, everything just packs very nicely. It's more efficient for the CPU. The data access is more regular. You always access values. Say you had an integer column, you always access them 4 bytes apart. So that's very nice for the CPU. And it's in general just easier to index into, right? Some of these might be implemented by just an on-heap Java array, which you can just index into normally, versus having to do complicated offset computations like you do in a row-based format, right? Where am I? Things like that. 2 is that it is more compatible. So many high-performance systems already use a columnar format. So an example of this would be NumPy, TensorFlow, Parquet. And to work with them, if Spark had an in-memory format, we could do this with 0 serialization and 0 copy. And it's not just by chance that NumPy and TensorFlow and what we're thinking are so aligned. It's just this is a natural solution to how to store data in an efficient way. So an example here would be most of your Spark plan, for example, is evaluated in Spark. And at the end of that pipeline, you want to call into TensorFlow, right? You want to use it for its processing capabilities. And then when it's done, you want to get it back and do more Spark computation, right? That's kind of a very pattern that Spark is kind of designed to solve. With Spark supporting an in-memory columnar format that's compatible with TensorFlow, this can be done without ever having to serialize across the boundaries. It just works together. And then lastly, looking forward, is that having a columnar format gives us more options to extend the system in the future, right? It makes it easier for us to do things like process on encoded data, right? So maybe the column is dictionary encoded, maybe it's bit packed, things like that. Those techniques would be pretty hard to do in a row-based format, right? Because you kind of have to, the data is non-homogeneous that way. We're looking at improving Spark's in-memory cache, which is also columnar, and this would make those two work nicer together. We can do delayed materialization in Parquet, offloading to GPU. I think this, in general, this layout will give us more options to improve in the future. So as part of this, we have also rewritten large portions of the Parquet scanner, right? So Parquet is kind of the most popular columnar format for the Hadoop stack. And again, similar kind of benchmark. So in this case, the number on the top is Parquet scan performance in 1.6. So again, end-to-end query time, we were able to scan about 11 million rows per second. And in the vectorized Parquet scanner, so directly scanning and materializing to this new in-memory format, we get about 90 million rows per second. So a similar kind of speed up as we saw with whole stage code gen, right? Roughly 9x faster. So this is promising and makes us think that the columnar layout will give us a lot of benefits. So putting it all together, so we're actively in development. So we have these two techniques, and they were kind of these bottom-up techniques, right? We looked at it and said, how fast could these components run? If we tried everything we can. And so, yeah, all of this is actively under development in master. And here I'm showing you the results of some of the TPC-DS queries. So this is the blog that you've seen in many places where we've taken a single fact table, store sales, and run some of the queries around that star. So the lines in blue represent Spark 1.6, and in red represent kind of the active under development for Spark 2.0. So you see kind of the summary is pretty sufficient. We see a 2.8 times performance improvement on the geo mean. So some queries benefit a lot more than others, and they're from, the query structure best matches what we've implemented so far. We expect those techniques to be extendable for the other queries as well. So in particular, Q55 gets something around a 4x performance improvement, and there are some other queries where the existing execution engine is particularly inefficient, where we see, say, up to 7 times performance improvement. All right. So what is the status? So we're actively developing this in master. We've been at it for maybe 2 months after some initial design work. Whole stage cogen is on by default. So if you just run the branch in master, it'll be turned on. The vectorized Parquet reader is off by default, but we expect to turn it on very soon. For the remaining, up to the end of the 2.0 milestone, now we're kind of back to the profiling techniques, right? So at the beginning I said that profiling typically doesn't get you this order of magnitude improvement that we're looking for, but it's very good for some of the remaining work. So what we're looking for here is to improve the quality of the generated code. It's not quite as optimized as the handwritten code that I had shown you in earlier slides, and to optimize the Parquet reader further. Right? Our kind of goal here is that for the Parquet 2.0, or sorry, for the Spark 2.0 release, we're going to get about a 5x improvement, so 30% better than what I showed in the previous slide, and then maybe another 2x improvement in subsequent Spark 2.0 releases to get kind of the order of magnitude goal that we are looking for. So yeah, we encourage you, please try it out. Let us know how it works for you. Again, actively under development. So in summary, in phase 1, for Spark 1.4 and 1.6 through 1.6, we focused on kind of the foundational techniques, right? Improved memory management, being able to take advantage of Java unsafe and off heap, laying the foundation to do code generation using some of the tools available in the Java stack, and then building some man. Oh, I don't. And then building some expertise in how to build more efficient cache-aware algorithms, right? A lot of the lessons we learned from sorting. In phase 2, right, we're doing these 2 techniques that I said, whole stage cogen and columnar in-memory support, with the goal that in the 2.0 lifetime, we should be able to get 10x faster, and also set us up to get even further improvements in the future, right? A lot of the techniques that we said are extensible, and we plan to take advantage of those. So that is all I had prepared. Thank you guys so much. So I'll be at office hours today at 1 at the Databricks booth for people who want to talk more about this. And I think we have a few minutes for questions if there are any. Yeah. Hey.
So my first question is, do you do Java code generation or any direct code generation? And do you incur the cost of a Java compilation of Java code?
Yeah, so the question was, do we generate Java source code or Java bytecode? Is there a compilation overhead? So currently we use Janino, meaning we generate Java. I'm sure there is a compilation cost, but because of the JIT and all that kind of stuff, it's really not anything we've measured. Yeah.
Does the cogen fuse together actions on the same data set? Or so like if I did a count and I did a count again, will those be done in one time or will it be done in two different readings of the data set?
So the question was, if I run kind of the same action again, say count twice, are they fused across them? Currently, no, they're not. So the techniques apply to a single kind of query execution. Yeah. One more time? Yep. Yep. Yeah, okay. Yeah, so the question was for that select query that I said, I think the one with the filter, can we take advantage of the data being sorted? Certainly. I think those are, the techniques I'm talking about here are orthogonal to what I'll say are storage techniques, right? I think in our ecosystem, particularly for Spark, we don't really own the storage, meaning that if the Parquet data comes in unsorted, we need to be able to deal with it well. And if it's sorted, we should be able to deal with it better, right? But certainly when we store some of the stuff in cache, we can maintain more metadata to optimize queries like that. Yeah. So the question is there any improvement for broadcast variables in Spark 2.0? Currently, not anything huge that we've actively planned. If you have kind of particular issues with it, please let us know. But in general, these techniques that I've talked about change the performance characteristics of Spark quite dramatically, meaning that existing components that were never bottlenecks are now very obviously bottlenecks. So that's kind of what we've been doing for the last few weeks and what we plan to continue to do for 2.0, right? After some of this initial work, we would profile kind of our hash map implementation, and it would take 90% of the query time, right? Just because we've kind of optimized other stuff so much. So I expect that things like broadcast variables, yeah, it's something we've looked at. We definitely know that it shows up quite significantly now. Yeah.
So does the declaration depends on the cache size of the hardware?
One more time?
But the declaration that you talked about, does it depend on the cache size of hardware?
How sensitive are we to the cache size of the hardware? I mean, in general, not so much. Right? Those sizes also don't change quite quickly. They tend to be pretty stable over time, and nothing we've done is really that sensitive to it. Yeah.
The RowBased format, is that completely going away? Or will it be replaced, or will that still be around?
That will still be around. There's still cases where we need it for particular operators that, but it's kind of should be localized to within an operator. So for example, if you do a join, your key, you want it in a row format where all the keys are contiguous.
What's the relationship on kind of the future of data sets versus data frames? Why do you need both of them? Why do you need any of them? And why SQL and RTDs are not enough?
Yeah, so the question is data sets versus data frames. Why do you need both? What's the relationship with RDDs? That kind of stuff. So the value of data frames over RDDs is that the execution engine knows the types and has better understanding of the computation you're trying to do. So all of the techniques I said requires that the system understand the schema, so they're not applicable to RDDs. For data frames versus data sets, data frames lose type safety over RDDs, right? You write your application, you want to use Java objects, and you want to access fields by name, right? You have a struct, I want to access fields in it. Using the data frame API, all you get back are rows, and you kind of access things by indices, right? You say, instead of saying, object.age, you would say object.getInt at index 0. So data sets is the solution to that. It builds on top of the data frame API, so you can get both. You can get type safety for user objects, as well as telling the execution engine enough about the schema so that we can apply these optimization techniques.
So data sets are indexed.
Or what?
Data sets are indexed access. Have they indexed access?
So data frames have index accesses. Data sets give you object access. Way in the back. Oh man, I can't hear you at all. Sorry, one more time?
Have you done anything which basically made improvements? Because I know that you would have written a parser, right? So have you done any sort of improvements with respect to garbage collection techniques, as well as with respect to the limitation? For example, it cannot handle more than 2,500 expressions, right?
Yeah, exactly. Whoa. So the question was, Janino has some limitations around code size and garbage collection. Have you looked into that? What's your plan to address them? So we've looked into a bunch of those. So performance does kind of fall off a cliff if you ask it to generate too much code. And I think in those cases, right, if your expression tree is incredibly big or your table is incredibly wide and you have many, many columns, the techniques I'm saying probably won't benefit you so much. So then we will fall back or use a combination of techniques to address those kind of problems. All right, I think that's all the time we have. So if you have more questions, please come to my office hours. Thank you.